Okay, so if we carry on looking at electrochemical reactions, this is the second video in the electrical chemical reactions. We've gone past the grade 11 revision. You may remember last year I got a nail and I placed the nail in a copper sulfate solution, and then I also got a piece of that magnesium ribbon and some coins and other stuff, and we wanted to see what would happen to the copper sulfate, what would happen to the nail or whatever was in there. And this was basically a redox reaction that was taking place, and it's a type of redox reaction that we call direct electron transfer, because you are putting metal in an aqueous solution and the electrons are being directly transferred between the pair of them. So a more reactive metal will displace a less reactive metal from its salt, and this is where I say, who wants to be an ion? In this little beaker here we have copper sulfate ions, which means we've got copper 2 plus ions and SO4 2 minus ions. And what happens is, if we come along with a piece of zinc metal, this zinc is a metal, but it would actually quite like to be an ion, because then it'll have a more stable electron structure. So the zinc comes up to the copper and is like, dude, take my electrons. And the copper goes, no, I don't want them. But the zinc goes, dude, take my electrons. And this is what happens. The copper gets kicked out of the solution. Okay, can you see the solution went from dark blue to light blue as there's less and less copper ions, and the copper ends up being deposited on the surface of the metal where the electron transfer is taking place. And in the meanwhile, the zinc ions go into solution, and zinc sulfate is colorless, which is why the solution is going colorless. And because this copper is coming out so very fine, it looks black. But if you were to put copper over here into a solution of zinc sulfate, absolutely nothing will happen. The colorless solution will stay colorless, because the copper goes to the zinc, take my electrons, and the zinc goes, no way, I've got a stronger electrode potential than you, I'm not taking your electrons. So that's why I say this is all a game of who wants to be an ion. And so the zinc is bossier than the copper, and the zinc becomes iron, and the copper has to go, oh no, I'm a metal again. Okay, not really, but you get the picture. The short story is, a more reactive metal displaces a less reactive metal from its salt. So if you have a look at what's going on here in that beaker, here's my zinc, here's my copper sulfate, which is in aqueous solution. There goes my zinc sulfate, and there's my copper metal. Okay, so in the copper sulfate it's Cu2 plus, but it becomes Cu metal. So it goes from +2 to 0. And the zinc was 0 because it was a metal, an element, and it goes to a zinc 2 plus ion, so its oxidation number is +2. So zinc's oxidation number has increased. It has been oxidized, but it is itself a reducing agent. The copper goes from +2 to nothing. Its oxidation number is decreased. It's been reduced, and it is an oxidizing agent. So this is how we have direct electron transfer. And basically, if you get out that table of standard electrode potentials and you start looking for zinc and copper, you'll see things that are reactive are higher, are above each other, depending on which table you're looking at. Remember those two tables, the one goes up, the one goes down. But you will see them in order. For instance, you know magnesium is quite reactive because we can burn it in air. And it burns with that nice bright white exothermic flame. And so you'll see magnesium is above zinc, and zinc is above copper, things like that. So the more reactive you are, it places you in that series of who wants to be an ion. Look over here. Okay, here is zinc plus 2 electrons going to zinc metal is minus 0,76, but copper 2 plus 2 electrons going to copper is plus 0,34, and this plus value means it's going to occur readily, that copper ions get booted back to copper. It happens much more readily than zinc ions getting booted back to zinc metal. If you look on that table as well, you'll see there's that little arrow that says increasing, reducing ability or something, and then you know this is better at reduction than this. Okay, so then that's what happens, or it's got better reducing agent. Okay, so then the next part is indirect electron transfer. And this is what we call a galvanic, see over here, a galvanic or a voltaic cell. And you'll become very familiar with this setup in the exam questions, okay? And now this is indirect electron transfer. If you have a look here, we've got the same things we had in the beaker. We've got some zinc metal and some copper metal, and here is some copper sulfate, and here is some zinc sulfate. But you can see they are separated into two beakers. They are separated by the beakers, but they are joined by a wire to complete the circuit and a salt bridge, okay? So we know that zinc would quite like to push its electrons onto copper, okay? And it can't do that directly because the zinc is not in the copper sulfate, but the copper is in the copper sulfate. So what happens is the reducing agent transfers electrons to the oxidizing agent, and it can do it through this circuit, this outside circuit. So you're harnessing the power of indirect electron transfer through a wire. You're focusing the electrons along a conductor. And then if the electrons move in the external circuit, this would become charged because obviously electrons have a charge. But we put in the salt bridge, and the salt bridge is full of ions, and the ions then even out the charges, so that the electrons move this way and then the ions will move the other way to balance it. So if you have a look here, this thing here, you saw it said a high resistance voltmeter. We can work out the voltage on the voltmeter using this table of standard electrode potentials, in the table of standard reduction potentials, sorry. So if you have a look, there's table 4A and 4B. Take one table, stick with one table. Pick whichever table you're going to use, because table 4A's got a strong oxidizing agent on the top and a weak oxidizing agent on the bottom. The other table is flipped. So the one table starts at fluorine, it's got hydrogen in the middle and ends at lithium. The other table starts at lithium, has hydrogen in the middle and ends at fluorine. Okay, and this value here on the right, this EO or E theta, this belongs to the forward reaction. So whatever this value is, it is the value for the forward reaction. Okay. The thing here to remember is that like reducing agent and oxidizing agents are really long to spell. So sometimes you'll see them abbreviated as that. And if you're studying, you might be tempted to abbreviate them to RA and OA. You may not do that in the exam. Okay, never, ever, ever, ever. It comes up often in the memos. 0 marks if you do this, or remove the mark for the formula if you do that. Do not use this abbreviation. So do not use RA or OA in the exam. You must write it out fully and just pick a table and stick with it. Those two tables are identical. Pick one, either 4A or 4B, and use it all the time. The other thing to remember on that table is that they're reversible equilibrium half reactions, okay? So when you get asked to write one of these reactions, at the end of the day, you're going to pick either the forward reaction or the backward reaction. So you have to figure out which reaction is taking place. You have to figure out who wants to be an ion, okay? Who is shoving the electrons onto somebody else who has to accept them and turn back into something that's not an ion. So you write either the forward reaction or the backward reaction depending on which two things you've got. So for instance, when you've got zinc and copper, you know the zinc's going to boss the copper around and the copper is going to become a metal, because the zinc is the stronger who wants to be an ion. Zinc really wants to be an ion and copper can't put up with the bullying. Okay, so let's have a look here at this, how to use the table of standard electrode potentials. This is quite important. You should maybe pause the video here, or I tell you what, I'm going to stop the video here and I'm going to restart it with how to use this table of standard electrode potentials.